Right now, as you watch this, the world is changing. A raindrop speeds up as it falls. A car accelerates, a price rises. Change is everywhere. But here is a question that puzzled brilliant minds for 2,000 years. How fast is something changing at a single, frozen instant in time? Not over an hour, not over a second, but right now. The answer humanity found is one of the most powerful ideas ever discovered. It is called the derivative. Let me show it to you. Let's start with something you already know: speed. You drive 100 kilometers in 2 hours. What was your average speed? 50 kilometers per hour. Speed is just distance divided by time. But your speedometer shows your speed at this exact instant. To measure speed, we need a distance and a time. So what time does a single instant use? If no time passes, you have not moved. The distance is 0, and the time is 0. And 0 divided by 0 is undefined. This is the paradox that stopped people cold for centuries. Here is the same journey, drawn as a graph. Time runs across the bottom. Position goes up the side. When the curve is steep, you are moving quickly. When it is shallow, you are barely moving. Pick two moments and connect them with a straight line. This is called a secant line. Its steepness is your average speed between those two times. Steepness in math is called slope. Slope is how much you rise, divided by how far you run. So slope is the change in position, divided by the change in time. Slope and rate of change are the same thing. Now watch what happens as we bring the second point closer to the first. The two moments get nearer in time. The secant line pivots, tracking a smaller and smaller stretch of the curve. In the limit, the second point merges with the first. The secant becomes a line that touches the curve at just one point. This is the tangent line, and the slope of the tangent line is your speed at that exact instant. Here is the intuition that makes it all click. Zoom in on any smooth curve, and it starts to look like a straight line. A derivative is what you get when a curve becomes straight, and you measure its slope. Let's write this down precisely. Take a point on the curve at position x. Step a small distance to the right. We will call that gap h. Now we have 2 points, and we can find the slope between them. Rise over run, the change in the function divided by the step h. This expression has a name, the difference quotient. Now remember our trick. We shrink that step towards 0. This is the definition of the derivative. The limit, as h approaches 0, of the difference quotient. We are not setting h equal to 0. Instead, we sneak up on it and ask what value the fraction approaches. Because so many people used this idea, it picked up several notations. They all mean the exact same thing. Don't let them scare you. F prime of x is quick to write. The dy, dx form looks like a fraction. It reminds us where it came from. A tiny rise over a tiny run. And in physics, a dot over a letter means its rate of change over time. Different symbols, one idea, the slope of the tangent. Enough theory. Let's compute a real derivative step by step. We will use the simplest interesting curve. F of x equals x squared. Drop it straight into our formula. First, expand x plus h squared. Substitute that in, and the x squared terms cancel. Every term on top has an h, so we can divide it out. And now the magic. There is no division by 0 anymore, so we let h go to 0. The h simply disappears. The derivative of x squared is 2x. Let's test it against the picture. At x equals 1, the slope is 2, a gentle climb. At x equals 3, the slope is 6, much steeper. At x equals 0, the slope is 0, right at the bottom of the curve. Doing that limit every single time would be exhausting. But look closely, a pattern is jumping out. The derivative of x squared is 2x. Of x cubed, 3x squared. Of x to the fourth, 4x cubed. This is the power rule, and it is your workhorse. Bring the exponent down to the front, as a multiplier. Then subtract 1 from the exponent. That's all. Feed an x to the fifth, and out comes 5x to the fourth. 3 more rules, and you can handle almost anything. A constant is a flat line, so its derivative is 0. A number out front just rides along, and the derivative of a sum is the sum of the derivatives. Now let's see why this idea is so powerful. As our point travels along a curve, the sign of the derivative tells a story. When the derivative is positive, the curve is climbing. We go uphill. When it is negative, we are heading downhill, and when the derivative is exactly zero, the tangent goes flat. That only happens at the top of a hill or the bottom of a valley. This is enormous. To find the highest or lowest point of anything, we simply ask, where is the slope zero? That is called optimization, and it runs on this one idea. So where does this show up? Everywhere something changes. Track an object's position and take the derivative. You get its velocity. Take the derivative again, and you get acceleration. Your car's speedometer is literally computing a derivative, moment to moment. In business, the derivative of a cost curve is the marginal cost. In science, it is how fast a population grows or a substance cools. Motion, money, growth, and heat all rest on the same quiet question. We began with a paradox. How do you measure change in a single frozen instant? The answer was to sneak up on it with a limit. Zoom in on a curve until it becomes a straight line, and measure that line's slope. That slope is the derivative, the instantaneous rate of change. From one honest question came a tool that describes the shape of change itself. There is a mirror image to all of this, called the integral, but that is a story for another video.
Please subscribe and thanks for watching.